Good afternoon. I'm Ross Stein. I'm president of the Tectonophysics section. And the honor and privilege of meeting and recognizing great scientists is the best part of this role. And so this afternoon, we get a triple play because we are going to present the award for the early career scientists and the Paul Silver Award, and of course, the Birch Lecture. And so what I'd like to do first is introduce you a little bit to Romain Jolivet, who's the recipient of the Jason Morgan Early Career Award. And for some of you who are very early in your careers, you may not know Jason Morgan is one of the reasons why we have plate tectonics. So it's certainly an august name for this important award. Romain, who is now at École Normale Supérieure, has advanced the use of interferometry, INSAR, to track variations in space and time of fault slip. Now, tropospheric effects have been the bane of INSAR because of the ambiguity between atmospheric and orbital contributions. And during his PhD at Grenoble, he designed and implemented a method to correct SAR for tropospheric effects, and during his postdoc at Caltech, he validated the approach globally. So this widely cited method is now implemented in the openly distributed software giant. So I'd now like to invite Romain to come to the stage to receive his award and to make some remarks. The professional photographer is the president-elect of the Tectonophysics section. That's the second most exciting thing we do. Okay, Romain.
Thank you, Ross. Well, of course, I'd like to thank the committee for nominating me for this award. It's quite an honor, especially considering the name of the award after Jason Morgan. I'd also like to give a particular thank to Jean-Philippe Avouac, who actually I learned by chance that he's the person who nominated me. That's quite touching, given how much respect I give him regarding his work and the way he took care of me when I arrived at Caltech as a postdoc. Other people to thank are the people who guided me through undergrad years, and especially Rodolphe Catin, who actually pointed me in the right direction. I didn't really know what to do, and he said, well, you should go and meet with this Roland Bergman person in Berkeley, who I thank also. And that actually got me started, and after that, my PhD advisor took over, Cécile Lasserre, so thank you very much to her. And I got to meet with amazing people like Gilles Pelzer at UCLA, Marie-Pierre Douin in Grenoble, then Jean-Philippe, also Mark Simons at Caltech, and finally the people in Cambridge who hosted me for 1 year. Finally, I'd like to thank all the friends who are in this room without who this job would be completely different and certainly not as fun. So thank you.
David Mainprice is the recipient of the 2017 Paul G. Silver Award for Outstanding Scientific Service. No award could be more central to AGU's mission of unselfish cooperation in research. David Mainprice's scholarship traverses mineral physics, tectonophysics, seismology, and has enabled an improved understanding of S-wave splitting, thermal diffusivity, phase transitions, and the relations among deformation, elastic moduli, and seismic properties. David, who is at University of Montpellier, was directly connected to Paul Silver. They wrote several important papers together, and anybody who knew Paul Silver knew how special a person he was, what the depth of his scientific contributions were, and of course the reason why we have the Plate Boundary Observatory is because of Paul. But more important in the context of David Mainprice's work is his intellectual generosity, his enthusiastic mentorship, and cooperation with students and colleagues. S. Misra from the Indian Institute of Technology quoted a Sanskrit aphorism, "Sharing knowledge gives humility, humility gives character." David has character. David, please come up and accept your award. I should say one more thing, which is that the Paul Silver Award is given jointly by tectonophysics, seismology, and geodesy, so there's more signatures on that plaque than your mortgage papers. And now, David Mainprice.
Thank you very much, Ross, for the introduction, generous introduction. Obviously, firstly, I'd like to thank my colleagues who proposed me for this award, Brian Evans from MIT and Andrea Tomasi from Montpellier. It is, in fact, very humbling to get this award associated with the name of Paul Silver, and in fact, I must also thank Natalie Silver for being present at this award. Paul, as you've already heard, was an extraordinary scientist, an absolutely exceptional seismologist, a genial colleague, and a great friend who we all miss. I would like to thank some of the people who taught me through the years, from starting my undergraduate education at Kingston Polytechnic, where most of the lecturers were lecturers, but they weren't researchers. So we got a tremendous amount of teaching and field work and practical work. And in my year, there were only two people who stayed in academic life, myself and Richard Law, who's Professor of Structural Geology at VPI, as it turns out. So after my undergraduate studies at Kingston Polytechnic, I moved to Imperial College London, where I was lucky enough to have Ernie Rutter as my supervisor for my master's thesis. This was an incredible experience for me because I'd never seen an experimental lab before, and so Ernie taught me more or less everything I knew at that time. And also, I did these experiments that lasted 2 months, which is rather unusual. And Ernie said, well, maybe you ought to learn how to use a computer to treat this data. So in the winter break, instead of going on holiday, I was seconded to the computer center for a week training course. And of course, I never typed in my life, of course, and they were on punch cards. I can tell it was hell, because every time you made a mistake, you had to throw away the card. Anyway, Ernie really was the person who set me on my path. He even taught me tensors as well. But at the time, I had no idea what I was going to do with this information, but it did come in handy later on. And of course, the third person I should talk about is Mervyn Patterson, who accepted me to do a PhD in Australia in Canberra. First of all, Mervyn wrote to Ernie Rutter to see what sort of student I was. So Ernie, being always in a hurry, didn't have much time to write a full recommendation. He just wrote a letter to Mervyn saying, so far he hasn't broken anything in the lab. So that was the recommendation I got. Mervyn was a very different character from Ernie. Mervyn was someone who had a very strong background in mathematics and physics, and he also had a very keen eye for detail. So he taught us lots of things in the lab. Of course, he knew his machines back to front, and it was a great experience. So I think also this sort of festive time of the year, I would like to thank the support of my family, my wife Brigitte, who's here, and I know that our smallest grandson is already dressed up in a Father Christmas outfit, ready for the magic day, and I wish you all a good holiday season. Thank you so much for this award.
I was a little worried he was going to thank Santa Claus. Greg Hirth's work has changed the way we think about physical and chemical processes in Earth materials. It's that simple. His investigations of experimental rock deformation has addressed the rheology and microstructures of a wide range of materials, including principally olivine as the mineral that controls lithospheric dynamics and its alteration to serpentine, and sometimes its alteration back. And these are crucial to understanding earthquake processes such as fault slip and subduction zones. Greg is a fellow of the AGU and the Mineralogical Society of America. He's a past president of the Tectonophysics section of AGU. He received his PhD from Brown University with Jan Tullis. He did a postdoc at the University of Minnesota with David Kolstad. He then spent 15 years at the Woods Hole Oceanographic Institution, where he also went to sea and developed new insights on the importance of serpentization in the lithosphere. And while at Woods Hole, through the joint HUI-MIT program, he collaborated with Brian Evans at MIT. In 2008, he returned home to Brown, where he is finally running his own rock lab, and he also now chairs the department, and I'm sure he is still receiving wise counsel, as so many of us are, from Jan Tullis. Greg, please come up. I know it's going to be a good talk, so we can do this now.
Oh, yeah. Ross, thanks for the great introduction and for the nomination to give this talk. It's a great honor. And I'd like to start off discussing these strength depth profiles. These papers were published when I was just starting undergraduate school, and I actually saw them in my structural geology class. I was fascinated by them, and ever since then, you know, these iconic types of diagrams have been used to explain all kinds of things and stir up controversy. There are a lot of data that suggests that something like this occurs, and there's other data that seem to cast doubt on aspects of these types of diagrams. So they serve a great purpose in starting off a conversation. So I'll start off with some of the optimistic insights that these have provided. So you can see here, this is a plot of stress versus depth, showing data based on thermobarometry and recrystallized grain size for giving a stress profile through the ductile crust. And here is a micrograph from a sample from the bottom of the KTB drill hole, in which you get a paleopiezometric stress from dislocation density, which matches right along that trend. The data from the KTB hole also provide some of the best evidence for the application of a frictional law, similar to Byerly's law, giving a strength that increases with depth in the brittle regime. So what are some of the issues? So a couple things have been pointed out for as long as those plots have been around. One of the things that's kind of interesting is that if you look at stress drops from earthquakes, they don't show any depth dependence on the average. So that seems to be funny if you consider a frictional regime with increasing stress with depth. And one of the ways people have recently been doing a lot of work explaining this is through dynamic weakening of fault zones or the effects of pore fluid pressure. So this dynamic weakening thing is really interesting because basically the concept is that during earthquakes, faults slip very rapidly and the friction drops very dramatically. And so most of the slip actually occurs at a coefficient of friction that's much lower than the static coefficient of friction. So in terms of plate tectonics, rather than thinking of a strength that's defined by the static stress, the long-term strength might be, or stress might be more similar to something like that. At the same time, even in places where we have data such as heat flow that suggests that the San Andreas Fault is very weak, the borehole data from the SAFOD project predict stresses or measure stresses consistent with a Byerly rule type friction. And while stress drops are generally quite low, it's intriguing that really high resolution data from the Parkfield area near SAFOD actually present stress drops on the magnitude of these stresses, indicating total stress drops. So this is kind of an interesting problem. You see evidence of low stresses in some places, and indeed plate tectonics requires low stresses to allow the plate scale deformation to occur. But we also see great evidence that the rocks are strong, and in other places that the stress drops, even where we think there is a low stress, can be quite high. So that there's a lot yet to be understood here. So when I was at the Oceanographics Institution, one of the things that occurred to me is that maybe some of the best places to study this type of process is the oceanic lithosphere for the following reason. So under a ridge, the material comes up, it melts, maybe dries out, translates over here where it cools. So think of the path. This rock has never been deformed in the brittle regime, so there haven't ever been any earthquakes for this material. It eventually cools where it will deform brittly, but it must be amongst the strongest rocks anywhere in the plates. So looking at the strength of this material should be a great way of testing the ideas of those stress depth plots. All right, so here's another problem. So when people look at this issue based on modeling of topography and gravity with the aid of looking at deflection of the oceanic crust around Hawaii, these types of models indicate the stresses can be greater than about 200 megapascals. Similarly, I told you about these rocks that come around here and break for the first time. Looking at the distribution of earthquakes that must occur owing to bending, as you see, thrusting events deep and normal events shallow, it's hard to work out a system where the stress is much larger than about 300 megapascals. So if you think about this issue, and here's our stress depth plot showing a bunch of flow laws for olivine, we have this stress barrier that doesn't permit all these mechanisms to operate. So there's an issue there. So over the last 20 years or so, I've been working to try to figure out ways in which to help understand these problems. And the approach that I've taken is both in the lab and going to the field, and then working with folks who study the geophysics of these types of problems. So the basic concept is in the lab, we conduct the experiments the best we can, and we look at the deformation processes and use that information to verify the flow laws by using theory about dislocations and diffusion. So the microstructures give us a tool then to relate the things that we see in the earth. And looking at the features that we see at the thin section scale, if we can understand the outcrop scale, that gives us a great way to bridge the gap in space and time associated with the extrapolation of the flow laws. And if we're happy with that, it gives us a way to then study these larger scale problems. So in doing that, over the last 25, 30 years, it's amazing it's been that long, I've been super fortunate to work with so many great students on all these different types of problems. Every week I come back and the things that are on my head are often the bureaucratic stuff related to being the department chair. And so Monday morning I'm kind of like, oh man, what do I have to do? But by every Friday, I'm fired up again. It's always great. All week long interacting with the students is really awesome. And the surprises that they come up with and all of the hard work and the fun we have, it really makes the job worthwhile. So, of course, you don't get to where you are today without awesome mentors. And I really want to highlight Bob Lynch, Jan Tullis, and Dave Kolstad, who all set me on my way at various stages of my career. And one thing that I reflect on all the time is that you never stop learning from your advisors, just thinking back of what they did and how you interacted with them and the lessons they taught you. So I really owe a debt of thanks to them for all the awesome mentorship and friendship. At Woods Hole, there was a really dynamic environment that was really amazing. And having the opportunity to work with seismologists and modelers was great. And in particular, I want to thank Henry Dick for having the insight or the crazy idea that it was a good idea to have someone who studies rock mechanics at an oceanographic institution. And Peter Kellerman, who I shared a lab with, who pushed me harder than anyone that I ever worked with to ask questions and push me in directions, make me look at rocks that I would never have looked at otherwise. And I really owe him a lot for all the amazing ideas that we've shared over the years. And also, as Ross mentioned, the generosity in both spirit and ideas that Brian shared made it worthwhile to make it through the 2.5-hour traffic jam to visit the lab quite a bit up in MIT. I have one other mentor. A lot of you might know that my dad is a guru in dislocation theory. And, it's not true. We never sat around the table talking about strain energy density or stacking fault energy or anything like that. And one of the things that we love the most is going birding together, like we're here in Costa Rica with my brother Mark. But over the years, we have struck up conversations, and it's really amazing to have someone to talk to. And for the first time now, we're actually collaborating on a problem to study twinning and plagioclase. So that's an exciting thing to do with your dad. It's also kind of funny, I'm sitting there thinking sometimes, my dad knows more about this than I do, so it's funny. All right, so off we go. So whenever I start talking about the application of flow laws, there's a few things I like to point out. So one of the important things to remember is the theoretical basis for the flow laws are really hinged on diffusion kinetics and elasticity. And an important thing about those things is they do not depend on time or scale. So in principle, there's a good basis to use the flow laws to extrapolate. So I put this big danger sign up here because at the same time we have to be honest with ourselves. We really are extrapolating samples that are this big. In thinking about extrapolating that to something the size of this room is a big step, but explaining the dynamics of plate tectonics from lab data is really something that if we're going to do, we have to do everything we can to justify the application of those laws. Another thing that this big explanation point is reminding me to tell you about is that sometimes in the community, people talk about the uncertainty in the flow law parameters as being so great that it's hard to say anything about the deformation in the Earth. And one of the dangers that comes from that is when you have an uncertainty in activation enthalpy, for example, in this Arrhenius plot, it might be pretty small. But if you just take this value of Q and change it by plus or minus 40 kilojoules per mole, you produce these dotted lines. So what you see here is those lines don't go through the data. And the mistake that a lot of people make in that case is that there's covariant uncertainty in the A parameter and the Q parameter. And when you account for that, you can see a much more reasonable extrapolation. The uncertainty is much, much smaller. But it's still 2 orders of magnitude. It's a big number. So anything that you can do to make 2 orders of magnitude smaller would be very helpful. So this is where geology comes in, and with the advent of great tools and geothermometry and other techniques, this is maybe one of the best ways to test the extrapolation of lab data. And when I went to Minnesota, it was really an amazing coincidence that I did my thesis deforming heavy tree quartzite, like David. And one of the cool things was that I went to Minnesota, and Christian Tessier had been working for years looking at naturally deformed heavy tree quartzite. And we looked at the samples together and were able to see these amazing correlations between the lab data and the data from the natural setting. So we struck out to look at the extrapolation, and when you do that, you can see that the pretty well constrained deformation conditions aren't really fit within the uncertainty of the flow law. So it kind of gives you a way to analyze uncertainty, but more than that, perhaps refine the flow laws to go through the data. One of the great things about grad students is that they come up to you and tell you that you're wrong sometimes. And those are, I always think, some of the most exciting days. And so over the last few months, Leif Tokel, who was trying to use the flow law that we calibrated back in 2001 to explain some of his data, and it didn't work. So he struck out to look at the problem in more detail. And when he took all of the published quartz data he could find and plotted them, normalizing to a constant set of conditions using the old flow law, he saw this amazing bimodality to the data set. In further interrogating the data, he then found that there were really 2 trends. These experiments were mostly all high stress or lower temperature experiments, and these ones were all low stress and high temperature experiments. And he also noted, after you separate these data sets, that the groups of data are also unique in that these guys show a CPO of quartz axes consistent with basal A slip in quartz, whereas the blue ones show evidence for basal A slip in quartz. So the prediction is, if you extrapolate these back down to the Earth, that you'll find rocks at a little bit higher temperature that show this type of fabric and a little bit lower temperature that show this type of fabric because of a crossover at this point. So we were lucky to have Whitney Baer as a postdoc in our department, and Leif noticed some data from her paper that I showed earlier. And when he plotted those data up with her well-constrained temperatures and stresses, he did indeed find, although you would have to squint to see the difference, the red line is indeed above the blue line here where you see this one, and the blue one is indeed above the red one where you see the basal flip. So the uncertainty in that, using that approach, you seem to really bring the uncertainty down a lot. And the fact that you can see the transition in approximately the right place gives great credence to the application of the flow law to understand the stress state in the crust. So that's a good lesson in extrapolation and temperature. So now the big problem in a lot of manodynamics is extrapolation and stress. So one of the big issues with extrapolation and stress is that there's a danger of having that low stress deformation mechanism different than the one that you're studying in the laboratory. And this is just an example showing the extrapolation of the stress dependence of olivine dislocation creep with showing the diffusion creep flow law with a grain size between 3 and 10 millimeters. So you can see, depending on which flow law you use, you might run into this diffusion creep mechanism, and your rheology would be completely different. So we run tests in order to create those flow laws, but it would be great also to have a natural setting to test whether or not the flow laws are applicable in the conditions where they are applicable. And so to do that, we rely on the same type of approach of looking at lattice-preferred orientations or crystallographic preferred orientations. And this is set up really well by the work that Shankarado and his colleagues have done, and as well as many of you out here who have gone out to look at natural rocks and run other experiments, to see the vast array of different types of CPOs that olivine actually produces. So the Silver Awards, Paul Silver, was one of the first people to really highlight how important this, what you might call a standard olivine fabric, was for interpreting geodynamics. But this vast array of different textures you can get in the lab and you can find evidence in the field suggests that, we really have to understand where and when these different processes are active and what produces the textures to be confident in the interpretation of seismic anisotropy in rheology. So what I'm showing here is work of Jessica Warren from her PhD at Hui and Phil Skemmer as a postdoc at Brown. And this is work that we did in collaboration with Peter Kellerman in the Josephine peridotite. So here is an amazing shear zone in the Josephine peridotite in which you can see these they're in the air here, but in the rocks you can see the banded nature of the peridotite that allows you to document the strain of the rock because of the deflection of the pre-existing fabric. And in addition, because it's an outcrop, you can actually define the shear plane that the deformation is occurring in. And this provided an opportunity to test how the CPO evolved with increasing strain. And in this shear zone, what Jessica found was that the CPO evolved in which the A-axis rotates towards the shear plane in a clockwise way for this dextral sense of shear. So you can see here, and in the high strain, this thing moves over here. And this is really consistent with the kind of standard interpretation of seismic anisotropy. In another shear zone, Phil Skemmer found this amazing correlation with one of the wet-type fabrics, the E-type fabric, in which case the A-axis actually rotates counterclockwise. So the lab data start off with the A-axis like that, and it rotates here. It never makes it back to the shear plane. His natural example showed exactly the same thing. So I took that as a remarkable observation that really strongly supports the scaling in stress and in scale of the dislocation process for olivine. And for people who've studied lattice-preferred orientations and models of them, know how hard it is to set up a suite of different grains that deform in such a way that would produce the texture that you see. And what's even more remarkable about these data is not only the general fabric that you see, but how it evolves with increasing strain. So it's a really, really strong support of that these dislocation creep mechanisms are active in the way that we deform them in the lab. One other thing that, this is probably better than it is in real life, but you see that the drier type fabric, actually the measured water content of the starting shear zone was a little bit higher, and the defining line was really essentially the same as that determined in the laboratory. My understanding is that more interrogation of this awesome correlation shows it's a little murkier than that, but in any case, the water content is about what you would expect this transition to occur, so it's a very strong indication of extrapolation in terms of water content as well. So now that we think that we're great and can take our teeny little samples and extrapolate them to about the size of this room, let's go ahead and extrapolate them in much larger scale to New Zealand. So here, it's kind of the self-similar nature of the deformation of the Josephine peridotite with New Zealand, and you compare that to shear wave splitting from the paper of Zeitlow, and you see the bending in of the shear wave splitting to become parallel with the alpine fault in a way that's consistent with dry lithospheric deformation at the base of the lithosphere at high temperatures. So it's pretty neat to be able to see that correlation all the way from the lab sample all the way up 25 orders of magnitude to New Zealand. Maybe it's only 24 orders of magnitude. Okay, so we're happy with flow laws. What about stresses? And so a lot of the data a lot of the constraints that I've been telling you about come from measuring stress in myelinites. And the basis for that is relatively straightforward. You do some experiments, you deform them at different temperatures and strain rates, you get different stresses, you measure the grain size, you get a log-log plot, and there you go. And in fact, you can find rocks that are at the very high stress end of this plot, and rocks that are off the scale into the mantle at lower stresses. So if we can really verify that this is a great tool, and people have been using it like wild since the 70s, then it will give us a lot more confidence in the other types of extrapolations that we do. So a little more than a decade ago, people started to really get concerned about the details of this, and people have been worried about it for a long time. There's all kinds of things that can screw this up. But one of the things people started pointing out is that the dynamic recrystallization process really involves a combination of grain growth mechanisms and recrystallization mechanisms, and the balance of these is going to set up the grain size. And indeed, a few years ago, David Berkovici gave this Birch lecture talking a lot about that and the importance of this process for controlling the plate boundary formation and plate tectonics. So one of the really important aspects of this is the temperature dependence of grain growth and dynamic recrystallization do not have to be the same. And if that's the case, then if you solve this equation for grain size, you end up with a temperature dependence from grain growth here, and then hiding inside of this strain rate term down here, there's also a temperature dependence. So recently, one of Whitney Bair's grad students has visited our lab to explore the recrystallization process in peridotite. And what she did was deform samples to different stress levels and then allowed them to relax and grain grow. And then she measured the grain sizes after different amounts of time in the relaxed states and measured the kinetics of the grain growth in those experiments. And one of the neat things that came out of that study is, first off, that her hydrostatic growth experiments matched her stress relaxation growth kinetics. And then the activation enthalpy of her experiments matched that observed by Dirk van der Waal in stress relaxation experiments done by Prem Chopra, I think, back maybe even a little bit after David was a grad student, or maybe even when he was a grad student. And what's amazing here is that the activation enthalpy here is about 520 to 30 kilojoules per mole, which is the same as that for dislocation creep. And what that suggests is that there's not a strong temperature dependence to the piezometry. And if you look at the data on the piezometric relationships, comparing some of these older studies by Shun Corrado and the one I just mentioned by Dirk van der Waal, you see indeed that the stress grain size relationship follows the same trend. So that's really good news. It gives us a way of saying, at least under dynamic deformation conditions, that the piezometry is a good tool for studying stress in an exhumed rock. Another thing that Dave Colstead and I worked out was a kind of an amazing thing related to the fact that the dislocation density in quartz depends on stress in a kind of a funny way to the 1.3 or 1.4 power. And if you just ask yourself, what is the dynamic balance between surface energy creation and strain energy density removal, and plot that up, that trend goes right through the piezometric data set. And that was another one of these impressive things to me that said, well, this might not be as complicated as we make it out to be, and it gives it more confidence in its application. So let's apply it. So when Whitney was a postdoc, she had an idea to follow up the amazing work she did with John Platt, looking at trends in the quartz regime, with looking at mantle xenoliths from the Mojave region. And one of the insights here, that the xenoliths from this SEMA zone were pretty recent, and that means these rocks are coming up from actively deforming lithosphere. And so you don't have the problem of this rock has been sitting around in the craton for a billion years. You're actually seeing a kind of a quenched microstructure from the deforming lithosphere. And the microstructures are beautiful, indication of dislocation creep. And when you plot up using the thermometry, you see that the stresses plot right in what you would predict for olivine flow laws between around 10 to the 14 to 10 to the minus 13 per second. So it's a really cool application of that. So basically what I've shown you is a bunch of data that suggests that this quartzite flow law and this olivine flow law work really well. So let's go on to the next problems where they get a little bit more difficult. The first thing is, when you look at the depth distribution of earthquakes in the oceanic lithosphere, people have known for a while, but it's only getting better and better with time, that there's a really well-defined limit to the depth, which is defined by something like the 600 degree C isotherm. So it would be great if we could explain that. So Margaret Boettcher was a PhD student who worked with myself and Jeff McGuire and Tom Jordan and Chris Marone. It was quite a committee, but we all fought over Margaret, and it was a good battle for each of us. And Margaret was great. And one of the things that she did is some really neat work looking at seismicity in the oceanic lithosphere. And at the time, the data for olivine friction suggested that it would start being stable friction would start at after like 200 or 300 degrees C, which is very inconsistent with what I just showed you. So she performed a suite of runs at different temperatures to look at the friction in the context of rate and state friction. And she found that at 1,000, these are rate drops of an order of magnitude. And so you see evidence for velocity strengthening at 1,000 degrees, velocity weakening at 800 degrees, and velocity weakening with stick slip at 600 degrees C. And then what we did was we went and thought about the adhesive theory for friction, and we had the insight that the places where grains were in contact should follow the pretty well calibrated olivine flow laws for low temperature plasticity. Well, we'll get back to that in a second, but they are amongst the best calibrated low temperature plasticity data. And so what she was able to show is a couple of things, that when you increase temperature, you see that this term, the d sub c term, increases. And the way to think of that is for a constant normal stress, as you increase temperature, the stress at the contact will drop because of the temperature dependence in the plasticity. So the asperities grow, so then when you do a frictional test, you see a larger d sub c in association with that. The other neat thing is that you can actually rearrange the flow law parameters for low temperature plasticity and predict the direct effect for friction. So if you think of rate and state friction again, you have your asperities and you instantaneously change the velocity, you'll have an instantaneous viscous response of those asperities. And so she compared her data, so here's the lower temperature values and the higher temperature values. So you see they increase, and given the uncertainty in the olivine flow laws, it was essentially a one-to-one fit, showing that the olivine flow law did a great job of predicting the rate and state friction parameters. So the next thing that we thought about is that she was deforming those samples at 1,000 degrees where she saw this transition at very fast rates. If you extrapolate those flow laws to the same stress state, you see something really cool, that at geologic strain rates, you see predict the transition occurs at 600 degrees, just like you observe in the data. So anyone who's been hanging out in the rock deformation sessions for the last couple years knows that there's just an enormous new amount of data studying low temperature plasticity. There's great theory, and there's great data, and there's great new techniques. And one of the kind of exciting papers that have come out about that shows this weakening with increasing scale. And one of the things you might predict from that is that the low temperature plasticity is at much lower stresses for geologic grain sizes. On the other hand, one of the things I'd like to point out about Margaret's data is that she was studying this process at a much higher temperature than where she's applying it. And I think one of the things that this points out is that in studying friction, you often, if you can, due to phase equilibrium, there's important trade-offs of temperature and strain rate that are important to take into account when you're scaling the data. So we have a pretty good model for this depth dependence, or the temperature dependence of friction. So we still have a problem, though. How do we get the stress that's high enough to allow the friction to occur? I'll get to that in a second. There's one more segue. I'm not going to talk a lot about this, but one of the other aspects of the issue of the strength of the lithosphere is that we've known for a long time that grain size plays a really important role in the effective viscosity of olivine aggregates. And another aspect of Jessica Warren's thesis was that she looked at these amazing ultramyelinites, following up on work that Gary Jerslow and Henry Dick and I did. And she applied the kind of techniques of piezometry and thermometry, and looking at the flow laws, she found strong evidence for a grain boundary sliding process in conjunction with the diffusion creep process. And applying those flow laws showed something that's really remarkable, that at around 700 degrees C, that these myelinites would have a viscosity essentially 3 orders of magnitude less than that of a coarse grain peridotite around it. And that's really strong kind of evidence for the type of models people are developing to understand the role of grain size in controlling the strength of the lithosphere. So every time I run into Peter Molnar, I've been lucky to work with him on a few projects, and he was also a great mentor for me when I was at Woods Hole. He lived in Woods Hole, and he would be around to trade ideas about rock deformation with. He always jokes that every year he gets older, olivine gets weaker. And it's true. The more we study this, the weaker it's getting. The same old strong stuff is still strong. There's just ways we figured out to make it weaker. And Mingli Zhao has a poster tomorrow demonstrating another new way of making it much weaker, looking at reaction-limited diffusion creep. And so you see here some of his data from shear experiments on olivine pyroxene aggregates. And at these conditions, you see that it's more than an order of magnitude lower viscosity than olivine with the same stress, temperature, and grain size, which is a pretty exciting result. And the other aspect of this is that the CPO he develops from this grain boundary sliding process matches that you can find in many myelinites with this type of banded structure with a B-axis maximum. So go see Mingli's poster tomorrow to find out more about that. Okay. So now let's get back to this problem of what happened to all of these high stress conditions. So at high strains and small grain sizes, we're okay in the viscous regime, but we still need to get this brittle deformation. And recently, another person I've been lucky to interact with over the years is Jeff Abers. And the first time I gave a talk in which I showed this plot, he raised his hand and said, "Yes, Greg, I understand there are all those neat earthquakes deep in the lithosphere, but it looks like they should be intersecting the ductile flow law, not the brittle flow law." And he's right about that. It's much easier for the rheological models in the lower part of these outer rise bending events to intersect a ductile rheology. So that got me thinking that maybe there's more to that than meets the eye, and we should think about what the role that those could play in allowing deformation at lower stresses, and that might help us with this problem that these really large stresses are too large really to allow the forces of bending and plate tectonics to occur. So I showed this plot earlier from this nice recent paper on looking at the data for the lithosphere-asthenosphere boundary constraints. And what I took out was this little thing here that said frozen in melt, and then high, I can't read it with my glasses, melt along the permeability boundary. So over the last few years, people have been noticing that there's a lot of evidence, or some evidence from models and geochemistry and seismology, that this part of the mantle isn't as pristine and unaltered or as uniform as we might think. So I'll show you a few examples of that. There's a nice modeling paper from Keller et al. In EPSL just a little while ago that looks at the melt focusing problem to the mid-ocean ridge. But in these models, they also show that a lot of melt doesn't make it out. And so these regions have as much as 1% porosity or more in these little pods that never get out of the mantle. So Chris Havlin worked with Mark Carmentier and myself looking at another problem that as melt comes up off axis and accumulates beneath the lithosphere, that you can promote dike propagation. And depending on the flux of melt, those dikes could either penetrate through the lithosphere or die deep in the lithosphere. Another example, Dan Lizaraldi and Jim Garrity and John Collins and I was a kibitzer definitely on this project, looking at seismic and gravity data in the Atlantic. And the seismic structure of the Atlantic lithosphere suggested that after a change in spreading rate, that 1.5 kilometers of equivalent melt was left trapped in the mantle. So if we go to the ophiolites, we see lots of evidence for this. There are huge parts of the mantle where you don't find a lot of dikes, but there's other places where you do see gabbro dikes and also peroxenite dikes. And here's an example of a cool feature that we found in Oman with these gabbro-norite dikes in peridotite, but you can see that there was deformation accommodated within the gabbro-norite. So here's an offset peroxenite here. If you look closely, you can see that the center of this dike is actually an ultramyelinite. And here's the plagioclase microstructure here. The olivine that's right adjacent to it is very coarse grain size of 500 to 1,000 microns, indicating at these deformation conditions of 600 degrees and 100 to 200 MPa stress that we get from the plagioclase, that the peridotite really isn't deforming at all. So putting that together with the data that we were just looking at, I began to wonder if you can envision a scenario where you have a weak dike that upon bending, that weak dike or peroxenite or whatever it is can deform, and you end up with large stress concentrations that allow the nucleation of earthquakes in the brittle peridotite around it. So I was talking to Laurent Montesi yesterday about this, and I had originally a really lame cartoon of this process in my talk. And Laurent said, I can model that in 5 seconds. And he was right. Within one AGU talk, he gave me a first model like this that showed a maximum stress of 300 MPa at the base of the lithosphere from bending, and then a weak ductile shear zone with a stress concentration of around 600 or more at the tip of it, which could nucleate the deformation. It's really, Laurent's an awesome guy. That was a great thing that he did for me there. And we decided that we're going to write a paper on that now, which is the second time that has happened. There was another time where we were in a seminar and we looked at a figure in a paper and we said, well, that's really cool, we should model that. And he modeled it like in a week, and then we wrote a paper. It was pretty cool. So Peter Kellman and I worked on a similar type of idea for understanding intermediate focus earthquakes. The idea there was to take those deep outer rise events and imagine that you've created a really fine-grained peridotite, and then upon subduction, when it heats up, that you get a shear heating instability because that fine-grained stuff deforms much more easily than everything around it. There was a kind of a magic temperature range of around 600 to 700 degrees where this would create a thermally induced viscous instability over a few seconds. You get a big stress drop. And in looking in the literature, you can actually find beautiful evidence for this type of thing. And this is from I think this is from Balmucia. There's a peridotite myelinite that has pseudotacholite associated with it. And these are actually glass pods that are preserved in the peridotite, which is really remarkable. So, we were envisioning that process would help explain the double seismic zone in subduction zones. But thinking about this process with having some weakening of the lithosphere due to the presence of trap melt. You can envision maybe thermally induced instabilities occur in this region as well, and maybe once those things get going, they can help knock off earthquakes in the brittle peritite as well. So those are my perspectives. I covered a lot of ground. What I really want I want to tell you that I'm convinced that this kind of integrative analysis supports the application of viscous flow laws for a wide range of materials. There's other materials that we've looked at that I didn't have time to talk about. And we find evidence that are applicable over a wide range of conditions in the lithosphere. The next point is that where you see obvious discrepancies, the way I think about it now is that we should really think of kind of these multi-scale modeling approaches, that the basis for the flow laws seems pretty strong. Maybe there's a scaling effect that we're not accounting for correctly, and thinking about models that incorporate that is maybe a neat way forward to understand a wide range of problems. And then the last thing was that it was really only through the strong collaborations with seismologists and modelers, field geologists, geochemists, and lab folks that this kind of integrative approach worked. And that, again, goes back to all the great colleagues and all the people that I didn't even mention at every meeting that I go to that make this such a fun job. And I just want to say thanks to all you guys, and I'll be happy to take questions.
I think we're all going to go home and put our friends and family members on a pressure temperature plot. I know just where to put certain people. So would anybody like to ask Greg a question? Jean-Philippe Bavouac.
So you made a parallel between viscous flow at the scale of the contact asperities and rate and state friction. And but it seems to me that your comments were more about how you can derive the A value and the D sub C, but you didn't comment on B. And on the fact that you can nucleate the earthquake depend critically on B. So could you comment on that?
Yeah, I didn't show it, but if you take the rate and state theory to include the evolution effect due to viscous creep, that the B term will scale with the stress dependence of the creep rate. And I didn't show that here, but Margaret's data, because in the low temperature plasticity flow law, the stress dependence is temperature dependent. And as you go up in temperature, it becomes more and more strain rate dependent. And in her B terms scaled well with that analysis. And you can read about that in that paper there.
Julie? Yeah, could you put that? Sorry. So Julie Morgan.
Greg, very nice talk. You raise the question of, not the question, you make the observation that you can scale from very, very small lab samples to explain the anisotropy of New Zealand, and then subsequently show us some very complex field outcrops where you have intruding magma that's preserved within the lithosphere, and that clearly is introducing some other heterogeneity. Right. And so I wonder how you reconcile the anisotropy, the seismic anisotropy, with the presence of these kinds of very complicated structures, which are also clearly accommodating shear.
Yeah, that's a great question. So the outcrops that we used to kind of test the scale dependence were like the best ones I've ever seen, right? They were spectacular, but they were very useful. If you look at the Omanophyolite as an example, there's all the amazing work that the folks in Montpellier have done. So there's pretty good record of the deformation by dislocation creep in the lithosphere there, but it is complicated by the presence of the dikes. There's no question about that. So the way I would look at that is that you need to think about those things together and look at the way you're analyzing the seismic anisotropy and interpreting it in that context. And one example of that actually is that FAME project that I mentioned about the amount of melt trapped in the lithosphere. So Dan and Jim really came to the conclusion that it was trapped melt as opposed to some anisotropic effect or cracking effect based on the gravity modeling in conjunction with the anisotropy. So it was actually the signals that they saw there that led them to that interpretation. So that's what I kind of meant is it just, if you just only look at it in one way and you say, oh, that doesn't work, so clearly the anisotropy isn't formed by dislocation creep or something like that, that's, you're missing some of the opportunity, I guess.
Yes.
So Greg, yesterday there was this great session with lots of good talks and people sort of taking aim at the Perls mechanism and proposing actually weakening with increasing grain size.
Yeah.
And I think back in the olden days, you and I had a flow law where there was weakening with decreasing grain size in the Perls regime. So today you presented with significant confidence results using old-fashioned Perls mechanism that seemed to fit data pretty well.
Yeah.
So could you, for this audience, please summarize what is the grain size dependence of the Perls law mechanism, if any?
Yeah, all right. Well, let's go back and look at, I'm going to torture you by flipping through. So these data look pretty convincing, right? These are at room temperature, and they're at very high stresses. And one of the neat things about this is there's this study by Idrissi that actually looked at the mobility of a single dislocation in a kind of a neat technique. And the thing that's neat about that is that kind of what you're seeing is at really coarse grain sizes that matches almost this single dislocation mobility. Now, one of the things that makes these types of data really complicated, if you try to deform these things to higher strain, they get stronger than the bejesus. They work harden so that the yield stress is really the thing that scales really well with grain size. So let's, since Peter asked that question, he's good at doing that kind of stuff. So in that session yesterday, where there were a lot of amazing data presented, it made me think of the outcrop we looked at here. And here we have a stress of 100 to 200 megapascals and a stress temperature around 600 degrees C. And yet we can't find any evidence of deformation in the peridotite here. So in one way for me to look at that, I'm more confident that while we can see, there's still a lot to be learned, and while we can get lower strength data with the type of modeling experiments from the low temperature plasticity, they're not going to bring us all the way down to 100 or 200 MPa at geologic strain rates at 500 degrees C. That's the way I interpret that. But I could be wrong.
Well, I'd like to thank, did you have a question? Just say who you are.
Oh, jeez. I'm still standing. Lars Hansen. I'm not going to comment on what you said. I had a different question that I just want to sneak in. So we could talk about it later. At the beginning of your talk, I just wanted to go back to one of the points you made and just have you sort of try and summarize your results in that context. You showed Whitney's stress profile with the quartzites.
Yeah.
And on top of that, you plotted, a hypothetical dynamic weakening line. So I'm curious, how do we think about the long-term strength of the lithosphere, where if there's some sort of frictional interface, then it could be really, really weak, but somehow those myelinites were supporting stresses that were much larger than it?
Yeah, it's a good question. So everyone close your eyes. So what Lars is saying is I put this cool red line in here, and one of the things that does is it chops off this higher stress viscous portion of the brittle ductile transition. So one of the very key aspects of the dynamic weakening process is that it requires frictional slip on a very narrow shear zone. So one of the things that's important is over the million-year time scale, you wouldn't predict strain localization into a centimeter-wide zone by the power law creep mechanism. So the trick around the conundrum you're developing is that what we could have is a higher stress viscous region and then a relatively quick drop off to this dynamic weakening type of stress profile. And I remember I've drawn these things probably on overheads back in the 80s or something, that they come up here and then they zoom over here to follow something like that. All right, so there's a couple neat problems that brings up. What happens if there's a rupture and it bonks into this thing? How far can it get in there? So that depends on the viscosity of that stuff and how wide the deformation zone is. So this brings into the context geologists and other seismic techniques that you could constrain the width of the viscously deforming zone. And, you know, I actually managed to give this whole talk without talking about water essentially at all. Come to my talk on Friday. But another aspect of that is how could really high pore fluids or fluxes of fluids chop off part of this beak by allowing low effective stresses that get rid of this part of the high stress zone. And so the kind of dichotomy that brings up might be that in some lower strain or lower strain rate regions you have this canonical view, and in rapidly deforming areas with lots of earthquakes you end up with a lower stress state over long term. But I think that's an open question, and I think this region down here is really an area where this kind of community's combined effort can make a lot of progress trying to address that.
Greg, thanks so much for making us all think about this important topic and giving us this great insight into how the Earth really works when we look at all scales.
Thanks a lot.